Yes, ma'am.
Yes, ma'am.
Okay. Uh, so let's start. It's already 5:05. Maybe how many of you joined? Okay. Okay. So if you remember, yesterday we are talking about a gross view about communication networks. There, we talked about how components can get. How we can attach components
Excuse me.
to a particular network, and they should have a particular address, particular port, and their
Hello, madam.
whole idea. Yes.
My friend want to join, madam. Can you accept it, madam? He sent request to join MS Teams, madam. Now,
Now, okay,
yes, ma'am. Hari
but
Kishore.
there is no pending request. See,
Left side, madam. Hari
Hari.
is request to join. Yes, ma'am.
Wait. Then I've already accepted. Seems. Let me check.
Around 4 sent request, madam. Yes,
I've
madam.
already accepted. See, maybe he can join now. Hari Kishore Misala, right?
Yes, madam.
Yes, I accepted. He is a member. He can join. It seems.
Okay, madam. I will call. I will inform to him.
Okay. Okay. So, if you remember, we are talking about the gross view of communication idea, and we have seen that what are the steps we have to do to complete the communication. That concept is basically divided into different layers. In a model, we talked about that OSI model. So this is the basic the layers of OSI model, where in each layer we have typically defined few specific few specific objectives. Now today we will start our discussion about embedded communication challenge, and here we will see, when we are talking about embedded communication, we will mostly talk about this initial two layers, physical and data link layer. And whatever today we will discuss, that is solely related to these data link layer. First, we will understand what are the challenges in this, media access communication that is defined in this data link layer, and what are the problem to adapt the same our traditional concept in embedded scenario. So today we will be only talking about this single layer, that is data link layer. So before that, a bit overview about embedded system. Probably most of you, most of you know this concept, but still a quick recap that when we talk about embedded system means some embedded computing unit, maybe some embedded computer, maybe some software unit, maybe some hardware unit that is embedded inside a bigger environment. That means this embedded computing unit is receiving input from the environment. Maybe it is receiving from the part of the environment it is residing within, or from some user interface, and it is performing some computation and sending output to that back to that environment or back to some other interface to other system, whatever it may be. Embedded means embedded within a bigger environment. Now, this computing or embedded system is the backbone today, as we know, the backbone of today's cyber physical system concept, where cyber physical system, as the name suggests, cyber physical system. So, Cyber means some computing platform. So if we consider this example, these computing platforms taking some input from these type of sensors, and after some computation, it is sending some input to this actuator or physical plant. That means if we consider this system, we can consider it as a cyber physical system because it has some cyber part, that means computing part, and some physical part that is taking the decision, that is working under the control. Maybe most of the cases that is working under the control of that particular computing platform or computing model. So that's why CPS, and when we are thinking about such CPS system, if we think this computing system is embedded in this bigger environment, then this computing actually is some kind of embedded computing. And that's why when we are trying to design or trying to think about such type of computation unit in embedded scenario, we have to think that since this is embedded, that is part of a bigger environment, it is very restricted in different terms, in terms of resource, in terms of network bandwidth, in terms of many other requirements are there. But first thing is that whenever we are talking about embedded system, we have to keep in mind few typical words. First thing is that it is very much restricted, very much resource constrained. Second is it is dedicated to a particular computation. It is not that when you are adding this computation unit, adding some embedded computation unit, you are expecting that this embedded computation unit will do lots of tasks. No, it is dedicated to some particular type of computation. So when we are talking about embedded, first one is dedicated, second one is resource constraint, and most of the time there are some, since it is acting as a controller of some physical plant, physical component, most of the time it is very much real time. What do we mean by real time? Okay, don't worry, everything is written in the next slide. Just you listen this, that real time means time bound. Real time doesn't mean it should be very fast. No, concept is not that real time means very fast or very slow. Nothing like that. The concept is real time means bounded by a certain deadline. That deadline may be hard, deadline may be soft. That means may be hard or may be soft. What does it mean? When we miss the deadline, in case of hard real-time embedded system, missing of deadline, that it should be very catastrophic. Like maybe in a satellite, or maybe in a power plant where you have some sensor that is detecting the temperature. And when that temperature is going beyond a certain threshold, this computation unit maybe compute how much it is more than a certain threshold. And if it is too much beyond a certain high point, then it should generate an alarm to, inform to other parts of the plant. Now, this may be an example of cyber physical system where if your computation unit misses the deadline to generate the alarm, to give input to the alarm within a proper deadline, then the effect may be catastrophic, and after a certain point, if that alarm is working or not, that is meaningless basically. So in these cases, the requirement is very hard. That means you have to meet the deadline, and real-time requirement. Sometimes we think real-time means very fast, where it is not about fast or slow, nothing like that. The deadline may be after 3 days. That is also real-time deadline. But the real-time should be, the deadline should be met. That is should be met. That is the concept. So in case of soft deadline, we understand, as the name suggests, okay, if you're missing the deadline, that may degrade the performance of your embedded system, but that is not very catastrophic. That is the difference. Okay. So this is the basic concept of what we do mean by embedded system. So it is written the same thing, whatever we have talked about. This is embedded system is a microprocessor based computer hardware. And this is dedicated. This is either, sometimes it is independent, but mostly it's a part of a large system, and it has the real-time computation requirement. Okay. Now, the challenge here is, when we are thinking about this is simple, maybe a temperature-based sensor and how it is giving input to a plant. And just doing a simple threshold related computation. These examples is very simple, whatever I have given to you. But nowadays, embedded systems are becoming more and more complex. As we have seen that last day, the example of a smart car. Your car is having everything. If you are sitting in the front seat and you are not putting your seat belt, it will give alarm. Your window, your back seat, your everything, it is connected by some sensors. And all these sensors, all these components are again connected to the car backend. Not only that, this car is again getting connected to some V2V network. Those are the terms now we think in terms of embedded and IoT scenario. Those are the basic applications where we think about driverless cars, where your car should have some kind of sensor that will sense that what is the speed of the previous car, or your car should sense whether your previous, it is maintaining a particular distance with the previous car or not, whether there is any pedestrian or not, what are the signals coming from the smart traffic light sensors. So basically, it is not a simple plant or simple device or circuit. It is running based on the input of this embedded computation. It is a huge number of embedded systems, huge number of cyber physical systems together connected, and it is in different domains. If you see this slide, you can see that embedded system nowadays in every aspect. It is in automation, it is in telecom, of course, in medical electronics like medical devices. In fact, nowadays people are thinking of taking help of cyber physical system to do the operations, right? Doctors should get a virtual environment to be created, and with the help of that environment, the medical operations will be done. So industrial control, automotive, everywhere, embedded system maintains its importance in every domain, and that's why the challenge comes is the heterogeneity. So whatever we have discussed yesterday in terms of our general communication, there we have just talked about computers and they are connected with your network. Now, obviously with these examples, you can understand. Now, it is not about the question of only connecting the systems or computers. It is connection of devices, things, sensors, components, plants, and different heterogeneous elements. And that's why here embedded communication is more complex compared to our general concept of communication. Okay. Now, when we have so much thing, to make it easy, what we can do, we can physically distribute these embedded systems. And for that, the advantage is that we can allow modular computations in different parts of embedded systems. And then we can connect these computation units with some sort of network fabric. That means now my challenge is not only I have to put some communication mechanism between this sensor, between this computation unit, between computation unit and plants, also between computation unit and computation unit with some other network layers. So every type of communication requirement is here. Now, this is just to give you the idea of what we mean by point-to-point communication links and what changes when we come to our network requirement, embedded requirement. So when it is we will discuss this afterwards also in detail, but just to give you an idea that when our smart cards were without CAN protocol, then we had some computation units, ECUs, and some other parts, other components are connected to these ECUs or to some other IO devices in this point-to-point fashion. You can see here ECU connected to IO. This ECU connected to this block. IO is connected to this block. These devices connected to this block, ECU, etc. So every point is connected to the other point with some dedicated communication link. Now, for smaller networks, smaller number of components, this is fine. But when we are having huge number of such blocks, maintaining such point-to-point communication, it's really challenging. So it is not practical, actually. That's why this is just one example how it changed the vehicular communication, present vehicular communication, where this single point communication is no longer required, and we use a simple shared bus where the communication, where the required components, they are getting connected, and communication is taking place through this single common bus, communication bus. Now you understand, when you have such type of dedicated link, this ECU, if it is interested to send some message or some information to this IO, it is quite easy. It can use this link and it can directly send that information to the IO block. But when these type of shared medium we are using, these ECU first need to should check that whether any communication is already going on in this shared bus or not. Because if already any communication is going on, and already some message is, maybe this block already sent a message, and this message is in the bus, then only if this ECU is again sending another message block, then there's a possibility of collision, that who will take the control of the bus. So when we are trying to simplify things, when we are moving from point-to-point dedicated links to these type of shared communication, shared medium access, then this is the most prominent question that who will get hold of the bus? How we can decide. And we will see, of course, this is not the case only in embedded communication, because this is a general concept of using this type of shared bus in general communication also. But embedded communication, when this requirement is prominent, our discussion will start from here, that we will take we will start thinking whether the general concepts of traditional communication to handle these type of shared bus scenario is sufficient to maintain communication in embedded scenario also. So for that, we have to know that what are the challenges, how we actually do this medium handling, shared medium handling in case of traditional communication, what are the limitations in that, and that's why what new techniques we are adopting in case of embedded communication. Okay. Okay. So when we are thinking about this type of local area network in traditional communication, most known technology, maybe you have heard this name, it is very common. This is the Ethernet technique. So Ethernet technique is heavily used, and it is a very known technique for workstation-like applications, our traditional communication scenario, where the communication is, this is important to know, aperiodic and burst. Huge communication, huge chunk of data at a certain time, some node is thinking to send to some other node. Like for example, now this is our class time slot. In this time slot, we are thinking to communicate, and from my system, my network, a communication is taking place to all of your workstation or to your laptop, something like this. So this is very aperiodic. This is not something similar to a sensor which is always trying to gather some information from a particular maybe some other input environment, and it is sending that to some computation unit. For example, if we go back here this sensor is constantly gathering some information, maybe periodically sending that to this computation unit to take some decision that may or may not be useful. Based on that, some input will be given to this physical plant. So you can understand, when we are thinking about embedded systems, embedded scenario, when we are using some sensor-based communication for monitoring, for control, this type of communication is not very similar compared to our workstation-like applications, where we have some time we are sending some chunk of data to the communication traffic, and that should be taken care of for that communication. Okay. So there is a fundamental difference. Am I clear? Just let me know if I'm going too fast. Okay. Just let me know if you have any questions. Okay, stop me and I will repeat that. So Ethernet, as we mentioned, that this is just this is the standard name of Ethernet. Sorry. This is the standardized name of Ethernet, and it is a family of word computer networking technologies that is used in LAN, MAN, WAN. I hope these terms now it is known to you. And when communication is taking place to Ethernet, the huge stream of data, they are divided into shorter pieces, and we call that frames. Similar concept maybe we have seen in the packetization also in IP. If we have huge stream of data, we divide it into packets and we add some headers on with it, and then we do the transmission. And in Ethernet, it is based on shared media networks. Due to we have seen, right, reduction is varying is possible if we go for shared medium. Like here, reduction is varying as well as cost, everything is possible. That's why we are starting our discussion with Ethernet, because now our complex embedded system has moved to shared medium concept. Now we are checking whether whatever shared medium networks we have in our traditional communication, whether they are suitable or not in case of embedded scenario. Now, rest are fine. We will talk it later about this, how these streams are getting packed into shorter pieces, what are the challenges in it, how we should decide. In the coming protocols or coming days, we will discuss. Today, we will only concentrate on these concepts, this shared media networks. How this shared media handling is done in Ethernet, and what are the limitations of that. Now this is the algorithm. Hope you can see it. This is the font, right? Okay.
Hello.
Hello.
Ma'am, what is 802.3?
Okay, this one. This is a standardized name of Ethernet. Okay, Ethernet is a family of wire technologies, and this is the standard, I mean, technical name of Ethernet. This is standardized by IEEE, and this is the name and number that is given. Okay. Okay. Next, we are today just discussing about how, if multiple, let's say, multiple components are there, and they are willing to communicate through a shared media, how Ethernet takes place. I mean, how Ethernet control decides that. Because it may happen, this, if they are component 1, component 2, and component 3, and they all are trying to get access of this shared bus at the same time. So that is not possible. I'm to grant this communication access to all of them. So how to decide that? Now, this is the algorithm that Ethernet follows. Sorry, I forgot to write the full name. This is Carrier Sense Multiple Access Collision Detection. Okay. Carrier sense means C for carrier. This is the carrier. Stations are sensing the carrier for multiple access, because all stations, they know that this is a shared medium and multiple access is possible, and they are trying to detect the collision, if there is a chance of collision or not. So when a station is intended to send a frame, okay, there are typical, there is a fixed number of K. Typically, you can see there, depending on your application, this K can be fixed. It is a number of attempts, how many times the station will try to send the packet. Otherwise, before declaring that there is a huge congestion, or and it is not possible to start the transmission. Okay. So initially, this number of atom K is equal to K is set to 0. Then any station, or we can say any component to that network, they apply one of the persistent strategy. Now, what we understand by persistent strategy, I will come to this slide again back. Just first understand the persistent method. Persistent method means, sorry, how many times, I mean, how the station or the component, they will start or wait when they detect some collision. Okay. So there are typically 3 types of persistent method in literature. This is one persistent or I persistent, that is immediate persistence. That means if any of them, 1, 2, or 3, any component, they are trying to send some data to the shared bus, they will continuously sense the bus. And if there's a typical way of doing that, they will send a particular signal, and they will check whether any communication is going on through this bus or not. Continuously sensing. If yes, they will wait, and once they will get the information that it is the bus is clear for transmission. That means clear transmission. Sometimes we call it CTS. Clear transmission signal is high. That means it is okay to send the message to the bus now. There will be no chance of collision. If they sense that the bus is idle, that station or that component will send immediately data to the bus. So this is called I persistent strategy. Okay. Next one is non-persistent. Non-persistent means it will sense. After that, it will not sense again immediately in non-persistent strategy. It will wait for a random number of slots, I should say, random time or random number of slots, and then it will again sense the bus, and this way when it will find the station or the component will detect that bus is idle, it is okay to send the message, it will send the message. So this is called non-persistent strategy. Next is p-persistent strategy, that is quite probabilistic. Probabilistic means initially it will continuously sense and then it will send the first message. Okay. After that, if it is p-persistent strategy, it will wait for 1 minus p slots again. That means it is not fully I-persistent, it is not fully non-persistent. It will wait for a 1 minus p persistent slots, and then again it will check whether the bus is idle or not, and then it will send a message. So these persistent strategies actually indicate how much time any station or any component they will wait before sending the message to the bus. Okay. So based on whatever strategies they are applying, based on that persistent strategy, they will wait. Then they will check for the bus. Okay. And they will say, yes.
Ma'am, please again explain this p-persistent.
P-persistent part, right? P-persistent part, see, the initial part is very similar with this I-persistent. That means initial at the start, it is continuously sensing the signal. It's sensing the bus, whether it is idle or not. And if it is not idle, it is again checking in the next slot. But once the first communication is getting started, it is working as a modified version of non-persistent strategy. In that non-persistent strategy means after sending one fragment, one message block, it is not sending the next message block in the next immediate slot, because there may be a chance of collision. Maybe if this station is using a particular time slot, there is a high chance that some other station may be using the next slot. So it is waiting for a few slots. How to determine this few word? If it is p-persistent, this is a particular probability, then this 1 minus p. This after these time slots, after a few time slots, with this 1 minus p probability, it is again sending the next message. This concept is quite probabilistic that there will be no possibility of collision. Because see, when maybe there are three stations, okay? In I-persistent or one persistent strategy, what happens? Continuously, maybe 1 and 2. Sorry, 1 and 2. Both are sensing the slots continuously. Whenever 2 is getting it idle, it is sending its data to the bus. Similarly, whenever, let's say at that time initially 3 is communicating to the bus, okay, and that communication is done. Now 1 and 2 both are continuously sensing the bus at that time and checking whether the bus is idle or not. But that time that bus was not idle. But once the communication by 3 is done, then bus is idle. And at that time, when immediately if 2 and 1 both sensing it idle, it is sending the data, their respective data to the bus, then obviously there may be a chance of collision, because both the sensing together at a time that the bus is idle and they are sending the data. That's why the immediate opposite side is that you are sensing it idle, you are initially continuously sensing, and then you wait for a random time. Now when a random number of slots. Now when we are talking about random number of slots, maybe this station 2 is waiting for R1, okay, and station 1 is waiting for some R2, random number of time. There is a very low probability that these two random numbers will be exactly same for this station 1 and station 2. So hence, this in case of non-persistent strategy, the chances of collision is really less compared to the first technique. Is it clear?
Yes, ma'am. Ma'am, how to resolve the problem if R1 is equal to R2?
See, everything is probability. Nobody is telling you that collision will not be there. But since we are talking about this station 2 is waiting for a random number of slots or random time, maybe we can say in a general version, and station 1 is also waiting for a random time, then there is a very low probability that two random numbers they are choosing or random number of slots they are choosing both the same for both of them, right? You are choosing for a given range, choosing of random numbers for both the stations, the same numbers, the probability is very low. So considering this concept, it is expected that in case of non-persistent strategy, this compared to this non-persistent strategy, the collision will be really low compared to this one persistent strategy. Okay. If there is other techniques, we will tell that if there is a collision, what to do and all that we will discuss. Okay, that we will come to it. That in very worst case, if that happens, that R1 is equal to 2. That we will explain in this algorithm. I will come back to that. But next comes this P persistent strategy. P persistent strategy means here it will initially for the initial part is very similar to this I persistent strategy, and after that it will wait for this P persistent time, that is not fully the random range, but a particular one and when it will send after a particular time slot, it will send it to a 1 minus P probability. Okay, so that is the concept of P persistent, where we are not considering the whole waiting range, because if you now think about non-persistent strategy, the waiting range may be too high. In P persistent strategy, that range we are decreasing, nothing else. Now we come back here. Whatever persistent strategy the station is following, it may happen there is still that you told that there is a risk that both are choosing the same numbers. So that means this if you follow this chart, that collision detected, there's a two paths. Either it is yes or no. Okay. If it is yes, collision detected, what will happen? This station will send a jamming signal. Okay. And this is the K. See, we have initially defined this K value, that is the number of attempts. That means if there is a collision, how the station can actually understand if there is a collision or if the message has not delivered to the respective destination point within a proper time. It may happen that the station in general, they have a certain threshold time. Within that threshold time, they expect some acknowledgement, and if that acknowledgement is not coming, they will understand maybe there is a collision, and that's why there is the proper communication is not offered and the message is not delivered. So they will again raise a jamming signal, and they will increase the number of attempts. That means already one attempt is done. Okay. If Ck greater than K max, that means the number of attempts made is greater than maximum possible attempts the station can make to transfer, to request for the bus, then it will abort and it will send a signal that communication is not possible. There is a huge congestion. Okay. If not, what it will do, it will choose a random number R between a particular range, okay, between 2 to the power K minus 1. And with this number, you can see, if you can see here, this is it will wait for a back of time. We tell it this back of time. How it will calculate the back of time? It is either R into TP, that is maximum propagation time. You can think of this. R means the number it is chosen, the random number within that range, and it will wait for a particular R into that maximum propagation time that it is known by each and every station of this framework. Okay, that means, again I'm repeating, every station will follow their persistent strategy, how they will wait and how they will send the message to the bus. Once that is done, after waiting, after following any persistent strategy, still if the collision is detected, the second level check is this maximum number of attempts. It will again increase the attempt counter and it will send that message again. But before sending that message, it will again wait for a particular back of time. How to calculate that back of time? It will wait again that random number again for the safety, because the random number you are choosing between these range and the number random number chosen by another station within the same range, obviously there's a very low probability that these are chosen by both the stations. These are same. Basically what happens when we apply a non-persistent or persistent strategy, and then on top of that we apply this back of time concept. Basically in both the cases we are applying concept of randomization. See, once we are applying it here and once we are applying here, right? So in both the cases, we are actually incorporating a concept of choosing a random number, and that way it is very, highly with low probability that in both the cases, both these two random numbers will be exactly same for two stations they are willing to transmit at a time. Is it clear? Wait. Is it clear?
Yes, ma'am.
Okay.
Ma'am,
Anybody
please
else?
explain again the use of ma'am, please explain the use of jamming signal again.
Okay. Jamming signal means it is quite straightforward, that some collision has been detected. That means it is identifying the one collision, but that doesn't mean it is stopping for the next level communication. Collision is detected, that is indicated by a jamming signal. But after that detection of collision, it is again this part is this part is attempting of the communication after detection of collision. See here, collision is already detected. Now this part is reattempting of communication. But when you are actually reattempting to send that message again, into the bus, you are again waiting some time associated with some random number. So randomization is applied in both the cases. One is in your persistence strategy and one is in your back of time waiting. And as I already mentioned that when two or multiple components or multiple systems associated with this bus, it is a very negligible probability that both the systems intending to send message to the bus at a time will choose same random number in both the cases. Okay. And once this is done, this back of time is selected, then again it will, after this back of time, then same loop will again run. Okay, again it will choose its persistence strategy. I mean, not choose, persistence strategy was already selected. It will, following its persistence strategies, it will wait some time, check for the slots. Again, it will send the message. Then again detect for the collision. If no detection, fine, that is a success of communication. If again detection, again increasing the number of attempts, waiting for the back of time, and so on. Okay, clear?
Yes, ma'am. What I'm asking is, do we really require this to send a jamming signal? Because if the message will be delivered, we'll be getting some acknowledgement. If we will not be getting acknowledgement, that definitely means it is a some collision has been detected. It has not transmitted its message. So, do we
You are
really
correct.
require? Yeah.
But think about this. If there is a constant attempt by let's say there is a huge congestion in this traffic, I mean communication traffic. Okay. On top of that, whenever they are actually, if you check here, when the transmission is taking place, that means you have already released some message or signal to the your bus. After that, you are detecting the collision. Okay. So that means if you send this jamming signal, maybe other stations will also get to know. Sometimes there is a use of this jamming signal that yes, there is a collision, and for some time we should restrain. In spite of my persistent strategy, in spite of my back of time, now I should release my message to the bus. But since we are receiving multiple jamming signals from multiple stations, so for some time maybe some extra delay can be added to release their respective messages to their communication channel. Because if itself there is a huge congestion, adding some more messages, that will actually adverse the situation. So to actually acknowledge to acknowledge about this collision and to inform about this collision, sometimes this jamming signal is important. Actually, we will see in some protocols how this can be useful. Okay.
Okay, ma'am.
So this is the strategy of CSM. Now we see if we think about our embedded scenario. This is our traditional scenario. If we directly want to copy this, because whenever we develop a framework, what do we try always? We try whatever we have.
Ma'am,
Yes.
ma'am, I have a doubt like which station would be sending the jamming signal here? Is it
Whoever
transmit?
is detecting the collision, see, any station, maybe station 1. Station 1 is doing this, all this.
So it's like it is also same like acknowledgement, ma'am.
It is, no, acknowledgement is different. See, acknowledgement is not incorporated in this blocks. Acknowledgement means whenever you remember in previous test discussion, what wait, I will show you about the acknowledgement. That is different. Wait. Where is it? I'm not getting it. Anyway, see, I will show you like this. Whenever you was maybe this way. Maybe this is your a sender, this is a receiver. Okay. Initially, remember we talked about when we had to put them in sync. Then the sender was sending some request signal and receiver was acknowledged. Okay. Here also, when we go for data communication, acknowledgement, where the sender is actually sending some frame or data fragment, that is a valid data along with some header it is carrying. Receiver may send one acknowledgement frame mapped with this particular data fragment or maybe some packet, whatever it may be, that okay, I have received that this number of frame or this data frame fragment or this type of packet. So that is the acknowledgement required from receiver to sender. Now, whenever sender sends a particular data frame, according to that is also depending on the protocol, how robust you want, because you understand whenever you are expecting some acknowledgement based on some of your data communication, you are adding some extra overhead. So it is not always. But that acknowledgement is that within a particular timing threshold, this sender is expecting this signal back, confirming that these data communication, that receiving of that packet or that data fragment has been done successfully in the receiver's end. If it is not getting that signal back, then it is considering that situation as a collision, because otherwise how that sender is just releasing its message to the bus. Otherwise, how it will understand that whether there is a collision or not, whether that data packet will reach safely to its destination or not. If it is not receiving that acknowledgement back, it is detecting that there is a collision, and then it is sending a jamming signal that there is a possible collision. Jamming signal is not that it is confirmed about the collision. It is there is a possible jamming of its respective message, and it is again trying to send back that message. Okay, acknowledgement means acknowledgement from the receiver's end coming to the sender. And this jamming signal means jamming signal is released to all other stations that there is a possible jamming. Clear?
Yes, ma'am.
Okay.
Ma'am, it is necessary to send acknowledgement signal.
Pardon? Pardon?
Ma'am,
Hello?
it is necessary to... Yes, ma'am. Hello, am I audible?
Yes. Yeah, tell me. Yes, I can. If it
Ma'am,
is necessary, yes,
to send...
of course it is necessary, very much necessary, because that will confirm. Actually, we will in our coming protocols we will see this. It is very much necessary. See, whenever you are sending a letter, also you want to get your acknowledgement. You want to get the acknowledgement whether your letter or your parcel it is delivered or not. But the problem in embedded scenario is that, as we told, that for embedded scenario, this is the limitations that we have to work within some cost sensitive scenario. That means we are resource sensitive. We have some limited timing, particular deadline, limited bandwidth. So everything is very much restricted. So within that, whether it is possible to send that acknowledgement or not, whether it is possible to accommodate that acknowledgement is not, that is very much case specific. We will see in some cases, we will actually, next week, we will start few discussion about some protocols. There, you will see that in some protocols, acknowledgement is there. In some protocols, the provision of acknowledgement is not there. It is, in spite of the fact it is necessary. But in some cases, and those protocols can be used, those type of scenarios where the chances of such collision, or it is very much maybe lightweight, very regular traffic is possible in that communication. In those cases, acknowledgement is not so much required because you are quite confident that your message will get delivered. In that case, you can avoid acknowledgement and you can choose your protocol according to that. So everything has a flip side. That is a concept. Okay. So just I want to finish this quickly. That based on that, so we have seen this when we are talking about this Ethernet. To adapt Ethernet directly in an embedded domain, the limitation is this realization of randomization, requirement of this randomization. Though this randomization is very much important to handle collision in shared medium, but if we are adding this much of randomization in our protocol, things are not deterministic. That means if you now want to calculate the timing requirement, since it's heavily dependent of number of few random slots, you cannot calculate properly in a deterministic way that now timing requirement of this type of communication scenario. For this reason, when we are talking about embedded system where the requirement is very deterministic, you have to consider real-time requirement. Your deadline is very hard. That in that way, Ethernet is not directly adaptable. Some other limitations of this embedded communication is that it is very much periodic traffic. Okay, periodic and very short messages. Remember what we talked about real-time constraints we have already discussed. Prioritize messages to allow quick access. Why priority is important? Because this part we will see tomorrow with another example, that when we are allowing some high priority traffic, we cannot treat that in a similar way as a low priority traffic. We will talk about that. Cost sensitive, we have talked about that this is very resource constraint, and that's why network bandwidth also limited. So we have to think about that. But this periodic traffic means if you think about a sensor generating a data, that is very periodic, but that is very short also. It is not as heavy as a bursty traffic. You are trying to send maybe with a mail, with a message, with a file, or with a video, this type of communication. That is not sort of bursty traffic. So if you think that if you now consider the packet overhead of it, you have a very small message, maybe message 1, maybe very 2 or 4 bits. Okay, 2 or 4 bits. I'm just giving one random example. And for that, you are adding so much header. At least source destination you have to add. You have to add some checksum. We will discuss what is all about. But just think about some header and source address, destination address. This much you have to add for your very small 2 to 4 bits traffic. Then you see for just sending a very small short message, the overhead you are considering is very huge. So the way we are actually considering data communication is in Ethernet with a simple fragmentation, that will not work directly here. Or here we have to think what are how we can packetize data very smartly to consider, to improve, to avoid these kind of overheads. Okay, now I think our time is up. Maybe tomorrow we will take up some other discussions. Okay, is there any question up to this point? Hello, are you there?
Yes, ma'am, no question.
Okay, so that's all. Maybe we can leave now. Tomorrow we'll discuss so what are the protocols, shared medium access protocols proper for embedded scenario. But as of now, just we understood that we cannot allow so much packet overhead in embedded scenario, and also we cannot allow the Ethernet to be adapted as it is with its random number requirement, random slot choice requirement as it is in traditional domain. Okay. So that's all. Maybe we can take the discussion next year. Thank you. Okay.
Thank you, madam.
Thank you, ma'am.
Thank you.